Okay. So if we rearrange this equation just slightly, we get this one. And now let's divide by the material balance, which remember is an expression that gives us, okay? And so what we're left with, we're also going to divide by FA naught at the same time. I'm just going to do it in one step. You're going to have FA naught over here. When you divide by the material balance, you get FA naught over there too. So what you're left with is now this derivative is no longer in terms of volume, but is in terms of conversion. So the whole idea here is to determine an expression for temperature as a function of conversion. And that's what we're working on. All right, and again, that might seem like it came from nowhere, but all we did is divide this equation by the material balance that we wrote down at the start. So we have the rate is a function of concentration, and we can write that in terms of temperature, okay? But now we want to write it in terms of the non-dimensional variable theta. So this is the rate written in terms of conversion. Again, this is specific to a liquid phase reaction. That's why we don't have anything in here like that epsilon parameter that you may or may not remember, which deals with the change in volumetric flow rate. After that, then we're going to relate this EA over RT term to theta. So what you get is that the K at any temperature is equal to the K at the initial temperature times just e to the theta. All right? Now we did this using a Taylor series approximation in this step. What you get by non-dimensionalizing the rate is now we can come up here and we can substitute in the rate that exists in that expression. By plugging this expression for K into there, since that whole thing is K, right? And so this is the expression that we get, and now we're going to substitute in some variables, and the variables are the ones that you guys see up on that slide, that rather confusing slide with this N over S and then this other expression S is equal to beta times gamma. That's where this comes from. Or this is where that comes from. All right, so we move E up here. This whole thing becomes N over S, and everything here is 1 over S. Just S. To try to put it into words, I will do that, but for now, just think of it as S. So I can write S, and again, this is just from this definition. It's just 1 over that. But I can also write it in terms of this beta and gamma. And so beta is this first term, gamma is the second term. Okay, everybody see that? I just take the invert because this is 1 over S. And I'm going to define 2 other terms, beta and gamma, where beta is this guy and gamma is this guy. All right, so what are these things? S gives the value of theta. And if we go back and look at what theta is, remember that theta represents the temperature change which occurs in a reaction. All right? And S gives the value of theta if you have a feed that's at T naught, which of course is in the definition of theta, it is allowed to react in an adiabatic reactor to some value of X. Okay? So it's the amount in an adiabatic reactor that the temperature increases. You can plot theta versus conversion. And remember that theta is T minus T naught over T naught. It's EA over R T naught. Okay? So again, it's representing a temperature change, non-dimensionalized, right? It's obviously a non-dimensional number, but the larger the number, the larger the temperature change, the larger the difference between T and T naught. And so you can get a value like this, or and what's changing here is I'm increasing S. Fixed N over S. All right? So if I'm not changing N over S, but I'm increasing S, then that plot does that. And so this is our runaway. The temperature just keeps going up and up and up as the conversion increases. The temperature never comes back over, right? So that's our runaway case. What is N over S? N over S N over S is the rate of heat transfer through wall when theta is equal to 1. And this is the rate of heat generation at the inlet. If I plot theta versus concentration, and I keep fixed S, and I vary N over S, I get the exact same shape. Okay? So you guys have already wrote this one down in your notes. If I increase N over S, but I'm holding S constant, the same thing happens. Now, runaway is defined as when this expression, theta versus concentration, does not go through a maximum. That's when you have a runaway reaction. All of these are not runaway reactions except this one. This is the only one where theta versus concentration does not undergo a maximum. That's when you have a runaway reaction. And so at the hot spot, you have that the change in theta with respect to conversion is equal to 0. And so you can solve this expression, d theta dxa, with either the material balance or the energy balance. And you can find for what values of n over s and s will you have a runaway. And that plot shows you some examples which have already been solved out. Right, because it's rate of heat generation at inlet, so it's very simple to find that. It's just the rate constant at the inlet, the concentration at the inlet, times the change in reaction, the enthalpy of reaction. So if we're looking at this plot, the different lines here represent different reaction orders. So let's take the blue line first, which is a first order reaction. I know it's hard to read. Any values of S or N over S which are less than that blue curve are runaway chemical reactions. Anything above that is stable. So if we look at it, what is it saying? If you increase N over S, remember that N over S is the rate of heat transfer versus rate of heat generation. So am I more likely to have a runaway at high or low values of N over S? Are runaway reactions more likely if I have fast heat transfer through the wall compared to heat generation, or the opposite? Right. If I'm easily transferring heat through the wall compared to the amount of heat that I'm generating, then I'm unlikely to have a runaway, right? My temperature is going to stay near the wall temperature, stay near the cooling water temperature. And that's what all of these high values are. As I increase N over S, see, no matter what reaction order I am, I'm going to go from a runaway to a stable reaction. All right, what happens if I increase S? What is S? A way to think about S is it's the ability of a specific chemical reaction to increase the temperature of the volume of the fluid that it's taking place in. Okay? So if I have a larger S value, am I more likely or less likely to have a runaway? Right. If that reaction is better at increasing the temperature, then I need to worry about a runaway reaction. And that's what's happening as I move from left to right. I go from a stable to an unstable regime. Okay, what about the effective reaction order? Why is it that when I go from n equals 0, let's start here. If I'm stable for n equals 1, and then I change it to n equals 0, I'm suddenly in a runaway system. Why is that? So this has to do with what we were talking about before break, right? Yeah, the reaction order, decreases. Right? If I'm here, I was stable. If the reaction order decreases, which of course you can't control reaction orders, but if the reaction order decreases, it means that that reaction has become less sensitive to concentration. Remember that we talked about before the break, that reactions which are less sensitive to concentration are more prone to being runaway reactors. All right? Yeah? Because the concentration is dropping as I move along the reactor bed, but the temperature is increasing. Okay? And so, which one wins? Which one is going to have a greater impact on the rate? The rate will decrease because the concentration is dropping, but the rate will increase because the temperature is increasing. Which one wins? Of course, you don't know that, but what does it depend upon? It depends upon the activation energy, which tells you how sensitive the reaction is to temperature. And it depends upon the reaction kinetics, which tells you how sensitive the rate is to concentration. And so if you're insensitive to concentration, then who cares that the concentration drops?
It really depends on which species you're...
Well, no, the concentration of the reagents drops. We don't need to specify which species we're talking about. Remember, we're talking about just power law kinetics. So when I say concentration, I'm talking about the concentration of reactants. That's what is dropping as I move down the bed of a reactor. Right? I had 10 moles here, but I'm doing reaction, so I go from 9 to 8 all the way down. And with that, the rate will drop. How much does the rate drop? Well, for a zero-order reaction, it doesn't drop. That's the problem. For a first-order reaction, it drops linearly. Second order, it'll drop quadratically, etc. And so if I have a reaction which is more sensitive to concentration, I'm less likely to have a runaway. And again, we had that on the board before we had a break. S is pretty much fixed. Okay? I can't change the reaction enthalpy. I might be able to add an inert to affect the heat capacity. I can't change the activation energy. I can change the inlet temperature, but that's going to have an impact on theta as well. So just trust me when I say that changing the inlet temperature is not going to affect this analysis. So really, I need to change N over S. So let's see. Do I want to increase or decrease N over S to go from a runaway to a stable chemical reaction? Increase, right? I want better heat transfer with my cooling fluid. Doesn't that just makes sense. Don't get caught up in what is N over S and up or down. Think about it physically. If I'm trying to keep a reaction cold, I want better heat transfer with my cooling fluid. So how can I do that? Well, I can increase the heat transfer coefficient. So you can do this by putting in things like fins or baffles. If you guys think back to heat transfer classes, I can decrease the diameter of my tube. Right? Decreasing the tube diameter will increase the amount of heat transfer area per volume. Not a lot I can do down here, except, again, I could dilute my mixture. If I have a lower concentration, that will help me. And again, we already had that. This first slide, or the first plot here, showed the effects of concentration, that we want to be at a low concentration. Lower concentrations are less likely to be runaway reactions. Right? And that shows up right there, because if I have a lower concentration, N over S is a larger value. All right. Any questions about runaway reactors? Okay, now we're going to talk about that. That topic is really out of order. I need to rearrange these notes next time. Because that has nothing to do with axial mixing, right? Now we're going to talk about axial mixing. Anyways. Hopefully it wasn't that big of a deal. So plug flow models assume this, right? They assume that everything has the same velocity no matter where it is within the pipe. So it neglects axial mixing, meaning that all of the motion of the molecules is related to convection, right? We don't have diffusion from a high concentration area to a low concentration area in the direction of the pipe. But it also assumes that you have fast mixing in the radial direction. So it's a little inconsistent in that way. But the fast mixing is what leads to a flat concentration profile in the radial direction, or a flat temperature profile in that radial direction. In a real system, you might have this plug flow environment until you hit your packed bed, right? And now suddenly you have very complex flow patterns. And you can have flow in the backwards direction, not just up and down, but also because of turbulence and mixing, you can have some backflow. Sort of rigorously accounting for this velocity profile is simply not done. It's too complex. All right? So we're not going to be worried about every single nook and cranny within this packed bed. Now when we leave the packed bed, again, you might return to a plug flow. So we've had this on the board before, but we account for dispersion in the axial direction by reporting a diffusive flux. This is the void fraction of the bed, because it's not all empty space anymore. This is the effective diffusivity in the axial direction. And finally, we have our concentration gradient, which is the driving force for diffusion. And so this is analogous to Fick's law. When we're, if we go back and we look at that chart that we put up of different reactor models, we're going to stick with the 1D direction, okay? So we're still going to be neglecting radial mixing to start, but now we're going to take into account axial dispersion. So the model is 1D plus axial. The material balance, now we have to include the diffusion term. This is our superficial velocity. I think everything else has been labeled already. And we can also plot an energy balance, because just like we can have diffusion axially, we can also have conduction or thermal diffusion axially. This is thermal conductivity. Again, here the E and the A mean the same thing, effective and axial. This is the mass per volume. Again, superficial velocity. This is a mass-based heat capacity. So we also have this generation term, where this is rate per mass, and this is the density of our bed, right? So to get us in, yeah?
In the material balance equation, can you explain why the rate actually takes off because it's consumed?
Yeah. It's because A is consumed, or this is the rate of production of A. But we often write that's all. And so what do you plug in here? Do you plug in negative KCA or KCA? Well, what do you plug in?
So you said we were producing it?
That's the rate of production of A. This is the rate of production of A. But you're right?
We're consuming it, right?
Sorry. I'm not being specific. That is the rate of production of A. This is the rate of consumption. Minus minus gives you the rate of production again. Okay? So what ends up there is the important part. Got it?
Which we're consuming, right?
No. The rate of production is negative, which is the same thing as adding the rate of consumption. But you're not adding here, you're subtracting. This is subtracting off the consumption rate. Again, why do we leave it in terms of the negative is because most people, when they write down the rate equation for A, put the negative sign right there. And so we just don't want we don't want to put plus RA there, and then you go, oh, it's first order, and then you put KCA. And you have plus KCA at the end. That would be a mistake. Does that make sense? All right. Hopefully everybody can read that. It's 4u over dt, t minus ta equals to 0. So if I don't have any axial mixing, I have just a PFR, right? Everybody get that? An ideal plug flow reactor. If the effective diffusivity were to somehow go to infinity, what you get is a CSTR. So if you have sort of infinite axial mixing, then you end up with a CSTR. Because, of course, if we had infinite axial mixing, we wouldn't have any concentration gradients in our PFR, right? We would just have an oddly shaped CSTR, which is magically stirred by diffusion. Of course, that's never the case. I just want you guys to understand, just like we've done before, sort of the relationship between these two things. Without that impeller, you're not going to have no concentration gradients in a plug flow or a packed bed reactor. Okay, so the solutions for these equations are non-trivial because the boundary conditions are rather difficult. We have two boundaries here. The problem is that they're very significant changes, right? I kind of have, if this is z equals 0, then I kind of have two very different environments at just to the left of 0 and just to the right of 0. And you can make the same argument over here that I have two very different environments at just to the left of the end of the bed and just to the right of the end of the bed. There's a lot of different boundary conditions that have been proposed to solve this problem. One set is set up for closed vessels meaning that there's no, I don't know if this is even worth putting up here. Struggle to find the best ways to describe this. But there's no reflection of mass or energy at the boundaries. Mathematically, the boundary expressions are, you have some concentration just to the left of 0 minus a concentration just to the right of 0. So that's your concentration gradient. This is your superficial velocity, and that is equal to the rate of diffusion. And this is, it's a boundary condition, right? So this is at z is equal to 0. For temperature, it's similar. You have the temperature difference just on the other side of the bed, on either side of the bed, but close to the interface. And that is equal to the thermal diffusion. Again, at z is equal to 0. The other one, the other boundary, is that at the end of the reactor, you have no concentration or temperature gradients. And that kind of makes sense, right? I mean, if there's no catalyst, then there's nothing changing the temperature or the concentration. So you have these 2-point value boundary condition problems. There are ways of solving this, but it requires sort of a trial and error approach. It's not something you really want to do. So you would only want to do these things when absolutely necessary. So when is that necessary? When do you have to worry about axial concentration and temperature gradients when you're working with a packed bed reactor? Well, let's talk about it. It's not immediately obvious when these axial concentration gradients will make a difference. So what are some of the things that it's going to depend upon? Is it going to depend upon the velocity, the superficial velocity? Probably, right? Is it going to depend upon the diffusivity? Probably, right? I mean, the larger the diffusivity, the smaller the concentration gradient. Same with the thermal conductivity. So, I mean, where I'm heading with this is that it's going to depend upon properties of the flowing fluid, right? And properties of the catalyst bed. So how do we deal with that? So you're going to need to calculate some Peclet numbers and come up with some idea of what is important. So Peclet for mass and axial. That's what the MA means, mass, axial. And as you might expect, we're going to have a Peclet for heat. And again, that's axial. And these are subscripts, even if I write them way too large. We get the superficial velocity. We have the void fraction of our bed. The diameter of our particle. And the effective diffusivity. So the things that we expected to see, okay? It depends on properties of the bed. What's the void fraction? How small are the particles versus large are the particles? What speed are we flowing our fluid? And what is the diffusivity of that fluid? I can also write this as UI, where this means interstitial. Oops. Velocity. And that interstitial velocity is nothing more than the superficial velocity divided by the void fraction of our catalyst bed. Okay? So what do I mean by that? Well, this is telling me how quickly am I flowing things through the pipe. This is telling me how quickly are things flowing through the interstitial regions of my catalyst bed. Right? Does that make sense? So if I have a very small void fraction, like 10%, then the interstitial velocity is going to be much larger, 10 times larger, than the superficial velocity. And again, that should make sense. If it's got to get the same amount of material through it, it's got to flow faster through those small holes. Okay.
What about the viscosity in here?
No. No, it's independent of viscosity. This is also equal to the Reynolds number times the Sherwood number. And it's typically on the order of sort of 0.5 to 2. Sorry, I should have put this up earlier. But Peclet in general is a relationship between convective transfer and diffusive transfer. And this is heat or mass. That's why we have two Peclet numbers. Like I said, I should have started with that. But that makes sense, right? I mean, we kind of, before we wrote anything down, knew that this would deal with how rapid is diffusion versus how rapid is convection in these systems. Will tell us whether or not the axial diffusion component of our convection or of our momentum of our transfer is important. All right. The heat one. Is that, and that is the Reynolds times the Prandtl number. All right, so the sequence is do something like estimate the effective diffusivity and the thermal conductivity from correlations, which, sorry, I answered your question a little bit incorrectly. Viscosity can affect diffusivity.
Yeah, I thought that's what you said before you introduced the
Yeah, yeah.
But it's not in the Peclet.
No, but it's in, where do I get a diffusivity from? Typically, you look up things like correlations between the Reynolds and the Peclet will tell you something about diffusivity, or effective diffusivity. But yeah, I mean, you'll see it when, in estimating diffusivities, you'll see viscosity. And we have a handout, which I think we can pull up real quick. It's like 20 pages later in the notes, but I have it open. So what we're looking at here is this is the Peclet number in the axial direction versus the Reynolds number. And these numbers here are just different sources, okay? So don't let that throw you off. And so you see that it's not extremely dependent upon the Reynolds number, but that this can give you a Peclet number. And from this, you can estimate the effective diffusivity given the particle diameter and stuff like that. This other one, again, gives you, no, this is radial effective diffusion, so we're not there yet. So what impact does axial diffusion have on the overall behavior of the reactor? So it typically decreases conversion. Why is that? Anybody think of a reason why having axial dispersion or diffusion would decrease conversion? Yeah. Yeah, exactly. It's because of backmixing. So you're diluting what used to be pure feed, right? You're diluting that pure feed. You're decreasing its concentration because things like products which you form further down the bed, can now diffuse against flow. Okay? So if it diffuses backwards, then the concentration decreases of your feed. All right. It'll attenuate hot spots. So if I have a hot spot, but then I think I have a hot spot, and then I consider the effects of axial mixing, sometimes that hot spot gets less severe. Why is that? No, not in this case. I mean, you're right that that will have an impact, but we can be simpler in this case. A hot spot is... Why is there an ant on me? A hot spot is temperature versus position, right? So now, how can I alleviate a hot spot? Well, I could transfer out of the wall transfer, right? But now I have a different mechanism where these hot regions can cool by heating the regions around them. So again, if I had perfect thermal conductivity, perfect 100% thermal conductivity, I wouldn't have any temperature gradients, right? Now, of course, that's never going to be the case in a plug flow or PBR type reactor, but in a CSTR, of course, that's what we get. And that's what I showed you earlier. As diffusivity goes to infinity, you get a CSTR. So this is how you can attenuate hot spots, by having that. Yeah.
So you need that there's more ways of effectively spreading.
Well, you already have the convection, okay?
Now you have it.
But now you had diffusion through the wall. Remember when we first did the continuum balance for temperature, we had to include that diffusion through the wall, but not in the radial direction. So it was a little bit of extra work. So we already had diffusion through the wall, or conduction through the wall. Now we also have axial conduction. So this isn't convection, this is conduction, or diffusion, if that, if you prefer not to mix up your heat and mass transport. But the point is that we have yet another mechanism, and of course, conduction or diffusion always works in the direction of our gradient, right? It always smooths out gradients. And so that's what it's trying to do here. It's going to try to smooth out that gradient. As the thermal conductivity improves, this gradient will become smaller and smaller.
Why couldn't it smooth it out before we had axial?
You can't like literally turn on or off axial mixing. But what I'm saying is, because axial mixing is a measure of how rapid conduction is compared to convection. So if you don't have axial mixing, that means that conduction is very slow. Or you're just neglecting it because convection is very high. Right? That's the whole point, is what we're trying to figure out is when is it important. But when it's important, it'll have these two effects, which will decrease the conversion. So another way to think about it is if you were to predict the behavior of a reactor without axial dispersion, you would get a higher conversion than the real reactor would behave. And you would get a more severe hot spot than the real reactor would have. But, of course, that conversion may not have really changed within any magnitude that you care about. And if it doesn't, then that's a situation where you can neglect axial mixing, which we're not quite. That's what we're going to talk about in the last 10 minutes. We've set it up. We've talked about calculating these Peclet numbers, but I haven't actually told you any criteria. So think back to internal and external mass transport, right? We had these similar arguments of when can we neglect external mass transport. And there we had the Mears criteria. Everybody remember? We also had an experimental protocol that we could follow where we would vary the velocity or the particle diameter and see if anything changed. But I don't think anybody put it down on the test when I asked. I thought somebody might. But the other way to tell if you have external mass transport limitations, right, is estimate the Mears criteria and see if it's within some value. That's similar to what we're doing here. We're trying to predict whether or not these axial diffusions or thermal conductivity in the axial direction will be important based on things like the Reynolds number and the Peclet number. All right, so let's look at some cases. So these are criteria for neglecting axial dispersion. This comes from a paper by Young and Finlayson. I always leave these references really incomplete because they should all be on the web page. So let's take it two cases. One in which the rates are max at z equal to 0. In other words, the rates monotonically decrease throughout the reactor bed. This is often the case, right? If we're talking about a first-order reaction where we don't have any autocatalytic behavior or any significant change in temperature, this is often the case that rates simply decrease throughout the bed. Then we can neglect dispersion if the rate at the beginning of the reactor times, again, this is the bed density, bulk density, and particle diameter, superficial velocity, and initial concentration. If that is much, much less than the Peclet number, okay? So we've talked about how to calculate that Peclet number. Now these are some things specific to our system which we can look at to determine if we have to worry about axial dispersion. Again, we want this to be very, very small. This is similar to the Domkohler. Keep putting the script T. It's not quite the same, but it's similar to the Domkohler number. And the Domkohler number is roughly proportional to a concentration gradient. Okay? Again, that's what we're discussing here is how rapidly is the concentration changing. That's what's missing from the Peclet number, right? The Peclet number doesn't know anything about the concentration gradients present within the system. So how can it tell you if diffusion is important when diffusions are proportional to concentration gradients? Well, this estimates the concentration gradient at the beginning of the reactor. And at the beginning of the reactor is where you will have the most concentration gradient if this is true. That is where your maximum rate is, right? Because the larger the rate, the steeper the concentration gradient at any point. Okay. That's for mass, obviously. It's similar for heat. Okay? So those are the two things to look at. But again, both of these criteria assume or are only valid when the rate is highest at the beginning of the reactor. Again, that's often the case. Okay? It's not always the case, but it's often the case. All right, any questions on this? Where these came from? Why are these important? Again, what is this representing? This is sort of a non-dimensional change in temperature which will occur at the beginning of the reactor. And this is the same thing here. This is a non-dimensional concentration gradient which will be present at the beginning of the reactor. And the severity of that concentration gradient tells you how important diffusion is going to be. All right. You can treat it independently. I mean, one is for, do I need to worry about axial diffusion of species? The other is for, do I need to worry about axial conductivity, right? Axial thermal diffusion. So you can treat them independently. All right, case 2 is when this isn't true. It's basically any other time. So rates are maximum at some other position, just anywhere. So why can this be the case? Well, imagine that I have a hot spot. Okay, so we discussed this already. If I have some region where I'm way hotter, it's not a guarantee, but it's possible that the rate will be higher at that hot spot than they were at the beginning of the bed. Again, it's not a guarantee, it depends. Other things, you can have something like autocatalytic kinetics. What do we mean by that? Well, that can really come into two forms. That can be if the rate is something like K over Ca, right? So that way, as I deplete A, the rate actually increases. So that's an autocatalytic reaction where the reactant is inhibiting the rate. Another example is if I have A to B, and the rate is something like concentration of A, concentration of B squared, or concentration of A, concentration of B over 1 plus the concentration of A times, I'm obviously not putting rate constants up here. So here I'm sublinear in A, right? But I'm first order in B, and I'm making B. So that means that the rate is going to increase with conversion. And again, here, the rate will also increase with conversion because for every 1 A I consume, I make a B, but B increases the rate much faster than A decreases it. All of these are exhibited by the same thing, which is that the rate increases with conversion, which is atypical. But in those cases, rates are not going to be their maxima at the inlet of the reactor. So in this case, we can neglect dispersion if the maximum value of dxa dz over the diameter of the particle is much less than the Peclet number. What do we mean by maximum? We mean anywhere along the bed, all right? So you have to analyze the entire length of the bed and determine if this maximum change in conversion with distance, really, is less than the Peclet number. And then for the thermal case, the left-hand side is predictable, as is the right-hand side. Oh, sorry. It's not predictable. See, I messed it up. This is another non-dimensional temperature. Both of these usually satisfied when you have a length over a diameter greater than 50. Again, this is length of the bed. This is the particle diameter. Aside from changing things like flow rate, one common way to avoid axial dispersion, and this is something that we do in academic settings quite often, is you add inert catalyst particles to the bed. This sort of spaces out your catalyst, right? And so it reduces the amount of heat generated in one spot. I like to think of this one more in terms of heat generation, but obviously everything I'm saying is the same with concentration gradients. So it reduces the amount of heat generated that's local, right? You're generating the same amount of heat, but spread out over a larger space. And that minimizes the concern of hot spots and axial dispersion.
So you worry less about axial dispersion?
Yeah, you are, but in a counterintuitive way, it's actually because it minimizes the effects of axial dispersion on the performance of the reactor. It's not to say that the axial dispersion is not still important. It's just to say that it'll have a lesser impact on, remember I said, what are the impacts, right? It'll have less of an impact. I don't think I want to talk about this last topic anyways, except to put up a little picture. But again, we're not going to talk about it in any detail. Having axial mixing present so I have an inlet temperature and I have a temperature at the outlet of my packed bed reactor. So for a given inlet temperature, I can have one outlet temperature. But if I increase the inlet temperature, there are suddenly 3 steady-state solutions. Again, this is for a packed bed reactor. And like we had to deal with in the case of the CSTR, you can have multiple steady-state solutions. This is stable. This is unstable. This is stable. All right. Now, again, we're not going to get into the details of locating these critical regions where you can have multiple steady states. But just be aware that because if you have axial mixing, this is only true when axial mixing is present, it can actually lead to multiple steady state profiles for your reactor temperature. And again, how does it matter? You know, how do you know which ones you end up at? It's based on how you start up the reactor. So any questions? Okay. I posted a homework last night. We'll have, which one was that, 9? I think we have one more, which will focus on these models, and then one which will be extra credit. I'm leaning towards something like the extra credit being 2 or 3% of the final grade, which works out to something like 5 or 6 points on a test. So, I mean, I think 5 or 6 points on a test is pretty generous. But you guys might not agree, then don't do the extra credit.